Chapter 6 discusses assessing the assumptions of the regression model. There are 4 basic assumptions involved with ordinary least squares, which is the type of regression that we've been doing recently. They all revolve around this disturbance, this residual, this error term. So remember, the error term is the amount of a miss, the amount of screw-ups that you had. So each individual error term is equal to the difference between the actual y and the y predicted by the regression. So if our regression is absolutely perfect, there would be, no misses. We would always get the exact right answer, but that's not always what happens. However, there are 4 basic assumptions that we need to analyze about this error term in order to see whether or not using OLS as we have is actually working properly, if this is the right type of model, all of that kind of good stuff. So the first one is we expect the average disturbance, EI, or average residual, to be 0, so that the regression line passes through the average value of y. This kind of automatically default happens. It's basically saying the expected value of errors is equal to 0. This default happens by the way that we've constructed the math that we use to get OLS, because we minimize the sum of squared residuals. So when we test for the assumption that the expected value of the errors are equal to 0, what we're really testing for there is that we have the model form correct. The second assumption is that the disturbances or errors have a constant variance, meaning that the variance is not dependent on any of the independent variables. It just happens to fluctuate randomly. The third one is that the disturbances are normally distributed. So again, not only do their variances fluctuate randomly, but also their values themselves. And finally, the fourth is that the error terms are independent of one another. Just because we missed by 2 last time doesn't mean we're going to miss by 2 this time, and so on and so forth. So why do I care about this? Well, if the assumptions are violated, my model could be 1, incorrect. I could have just gone, ooh, look at this fun, fancy computer that can run regressions, yay, and just plugged in stuff that made absolutely no sense, and when you plug in crap, you get crap. Or 2, it could actually be really logical and okay for forecasting purposes, but, it might not really be good for interpretation purposes. Meaning I may be able to use it to make a prediction to actually predict y if I violate one or more of these assumptions, but I wouldn't be able to use it for hypothesis testing purposes. I wouldn't be able to use it for the purposes of, interpreting that beta. So saying for each additional unit of X, Y will increase by whatever beta is. That wouldn't really work if I have violated one or more of these assumptions. So how do I know if I violated assumptions? Well, there's 2 steps that we can do. The first one is to plot the standardized residuals and look for any patterns which demonstrate a violation of one or more of these assumptions, and we'll talk about what those patterns look like. And the second is to perform a specific test for each assumption. So we're going to talk about 3 statistical tests that we're going to use for these 4 assumptions, testing these 4 assumptions. So how do I plot my residuals in Excel? Here are the steps: data analysis. You'll click residuals and standardized residuals, and then you'll just do a scatter plot of each independent and dependent variable against the residuals to check for any kind of pattern. So in most of the examples that we're doing in this slide presentation, they're simple regressions, but you would have to make sure to examine the residuals relative to each independent variable as well. That's also going to be key. Here, obviously, there's only going to be one chart, but since there's only one independent variable. But make sure if you are running multiple regressions, that you remember to examine the residuals against each independent and dependent variable. Here are the steps in SPSS. Again, it's going through and basically building a scatter plot. And again, we have the reminder to make sure that you do this for each, use that scatter plot for each of the independent and dependent variables. So testing assumption 1, it's testing the assumption that the expected value of the error terms are 0. And since OLS forces the mean of the residuals to be 0 anyway, as a function of minimizing the sum of squared residuals or sum of squared errors, what we're really testing here is whether or not the linear relationship that we chose to model with a regression equation y equals beta 0 plus beta 1 x1 plus blah, 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 plus our error term is in fact correct, meaning that a linear relationship was in fact correct. And the way that we're going to do this, really, the only way we're going to examine it is just going to be to look at our standardized residuals and look for no pattern. So they should be completely random and centered around 0. These standardized residuals should be completely random and centered around 0, and as long as that holds, then we're fine. So the first example is Telmark 6 data, which looks at 20 telemarketing employees and the number of calls that they make based on the number of months that they've been on the job, and we see that as the number of months increases, the number of calls increases, but at a decreasing rate. So when we first run that initial scatter plot, just x against y, we're seeing here that this is more of a polynomial relationship, specifically a quadratic relationship. So x is increasing, but at a decreasing rate. And that's characterized when I plot those standardized residuals. I also see that parabolic term start to appear in there. So that's going to be telling me that I'm violating that assumption. And here I just have that, those same things drawn out. We see a histogram of the standardized residuals. So they look relatively normal, but when we look at those actual, the third graph here where we're actually plotting out the residuals, you again see that parabolic relationship in there. So that's telling me that a linear relationship probably wasn't appropriate. So the way I should correct this would be to run a polynomial regression. In this case, it would be a quadratic regression. If I see, clumpiness on my x-axis, then I would need to run a logarithmic transformation. If I see clumpiness on my y-axis, I'd need to run a logarithmic transformation. If I see, I can also see a reciprocal, increasing at a decreasing rate. All of those kinds of relationships that we talked about for model transformations in Chapter 5, I could see those in my standardized residuals, and that would tell me, oh, wait, this linear regression didn't make sense. Really, I needed to perform a transformation before I ran this. So that's just what this is talking about here. So if you see any of the patterns in the residuals that you saw initially in that first scatter plots when we were talking in Chapter 5 about appropriate model transformations, then go back and say, oh, I needed to transform something. So again, this is where it's going to be really, really important to run to plot your standardized residuals against each of the independent variables, because you could see that there is a quadratic relationship in x2, but x1 there is no relationship that you're seeing, or there could be a reciprocal relationship in x3. Who knows, maybe x4 needs to have a logarithmic transformation done to it. So each of those individual plots really becomes key in trying to spot the patterns in them. If you just look at the standardized residuals against the predicted y value, then you're not necessarily going to be able to spot that pattern. So be really, really careful to make sure that you do each of those individual graphs. Okay, now this is just talking about, was your correction really better? And it focuses on the same kind of logic that we talked about in Chapter 5. So if your transformation really was better, then your R squared should increase and your standard errors should decrease. So there's no reason to necessarily go through this F test. You may see this occurring in some of the papers that you're reading. This is, the official way to check, is your correction okay? But as far as I'm concerned, just showing that your R squared increased and your standard error decreased would be fine. Okay, so, here's just that example showing, hey, look, we did better, therefore this is good, and then we can run through and do that F comparison test to confirm that the transformed model was in fact better. Assumption 2 is that the variance of the error terms is constant. So the visual method is to plot the standardized residuals and look for no distinct pattern. You're going to hear me say that for every single one of the assumptions. So that's always going to be your first step. You can also plot the residuals against x for a simple regression or for each x for the multiple regression. Now, I'm pointing it out here because this is going to be really important. If the residuals increase as any of your x's increase, then you have a problem. I'll repeat that. If the residuals increase as any of your x's increase, then you have a problem. That shows you heteroskedasticity. So that will be a cone-shaped pattern. If the residuals increase as x increases, you'll start to see a cone-shaped pattern in those residuals, and that is bad. That is what we don't want to have happen. That is heteroskedasticity. Now, that can occur in any of your independent variables. So again, it's really important to plot your residuals against each of your independent variables. And it doesn't matter whether you plot your standardized residuals or your regular residuals. The only difference is that the standardized are going to be bound between -3 and +3 roughly. Okay. And that's because they're calculated by dividing the residual by its standard error. Now, although the OLS estimator will remain unbiased, meaning the coefficients wouldn't change if there is heteroskedasticity, the standard error and the confidence intervals, as well as the p-values and hence the p-values for your t-statistic and then hence all hypothesis testing, all of that would be off. So you could still use it for predictive purposes, even if you do discover heteroskedasticity, but it really wouldn't be good for interpretation purposes. So here's our example. We're using FOC sales 6. We're looking at the relationship between between months and sales for a fiber optic company, and we have data over 265 months. And here you can just see when I do even just my general scatter plot of x versus y, I have this cone shape starting to appear. And that cone shape also appears when I do my standardized residuals against my predicted, so my residuals against my predicted y, and then when I do my residuals against my x. So since there's only one x here, that's telling me that I am violating assumption 2, meaning I have heteroskedasticity in my independent variable. Now here there's only one independent variable, so obviously I know which independent variable is going to be causing it. I can also confirm this using my Brausch-Pagan test. And I'll show you how to run this test in both Excel and SPSS. Again, it can be performed for both simple and multiple regressions. So steps in Excel, run OLS and compute the regression residuals. So not just the standardized, you'll click on residuals that you want residuals and standardized residuals. There's nothing wrong with just looking at the graphs of the standardized residuals, but in order to run the Brausch-Pagan test, don't use the standardized residuals, use the regular residuals. Then regress the independent variables on the squared residuals. So your next step is going to be to square the residuals. Again, be really careful not to use the standardized residuals, but to use the residuals themselves and all of the independent variables. So regress x on y. So y is going to be your squared residuals, and all of your independent variables are going to be your x's. And you're going to calculate this BP statistic, which is called LM, Lagrange multiplier, which is equal to n times the r squared value in there, the r squared value of this new regression. And HO is the residuals are homoskedastic, meaning there is no problem. And HA is the residuals are heteroskedastic, meaning that there is a problem. And the way that you're going to look at this, you're going to just examine the p-value, and you're going to get this p-value using the function chi-dist, that BP statistic, comma, now here it says 1 because there's only one independent variable, but you would actually change that 1 depending on the number of independent variables that you have. So, if you have 4 independent variables, you would you would use chi-dist, that Brauch-Pagan statistic that you calculated above, comma 4. And that would give you your p-value. And you would do your standard interpretation for your p-value less than 0.05, reject HO, meaning that there is a problem. Greater than 0.05, do not reject HO, meaning that there is not a problem. Okay, so here are the steps in SPSS. Now, unlike some of the other things that we do in SPSS, this one you actually have to run through and create this. So I have all of the steps here. I also have a video that shows you how to do this, but you can see at the very end, step 7, the BP stat is n times the r squared of this regression. Calculate its p-value using the chi-squares distribution. So you're going to have to go through and do the same thing. And I would suggest consulting the video on doing this, and then you can have these steps printed out so you can see exactly what each of the steps are. Okay, so here are those calculations where you actually go through. I'm showing you just the comparison. These are those final models that are run. First in blue is what you get from running that, the regression of residuals squared against independent variables in Excel, and then we have the SPSS output as well, and then in green we have just the comparison between the two. So, your numbers are going to be off slightly, but you'll come up with the same basic conclusion. Now, note, degrees of freedom are going to be a little bit different. It's just a function of the way that the tests are actually run using Excel or SPSS. So when we ran this in Excel, we only had one independent variable. If you go back through the steps in SPSS, we actually have 4 independent variables that are used. It ends up, in this case, dropping one of them because it had perfect multicollinearity with another, and that's just an instrumental variable transformation. It's giving you, running in this in SPSS, you're getting a slightly more exact value because you're doing some additional transformations of each of the independent variables. So again, that's going to be highlighted in that video for you there. But in both of these cases, we're going to come up with the same result. Obviously, we saw that cone-shaped pattern. Our p-value is really, really, really close to 0. We're going to reject HO, and there's definitely heteroskedasticity here. So then the question becomes, well, how do you fix it? Here are the steps for White's heteroskedastic corrected standard errors. It's done for each x and therefore each coefficient. This corrects our standard errors, but also the t-stats and p-values and the confidence intervals used, so that we can use them to make appropriate interpretations. Because remember, if there was heteroskedasticity, your model was unbiased, meaning your coefficient was fine, but it was the standard error which was wrong, which caused the p-value to be wrong, which caused the t-stats to be wrong, which caused the p-value to be wrong, which causes your confidence intervals to be wrong. So you're going to make the correction using these steps in Excel, and then the interpretation would be the same as you would have for for any kind of OLS regression that you would go ahead and run. So your coefficients would be the same. The standard error is the square root of White's variance. This is White's variance. So the sum of each of the individual x observations minus its mean squared time that quantity times the residual squared. That's going to be the numerator, and the denominator is the same as that numerator, but then squared again without the addition of those residuals. So I have an example showing you how to perform that in SPSS. The t-stat is going to be calculated in here. I mean, you can go through and see the t-stat is this t-stat down here in the orange box, because that p-value is going to be that p-value two-tailed, because that t-stat is based on the testing HO that beta is equal to 0. So this will basically just make any corrections for heteroskedasticity and allow you to go through your normal interpretations again in that green box area. But be careful, because you need to do this for each and every independent variable. So here's, just going through that assumption, going through that example and showing you how to do it. And you can see that I broke it up. So I did the residuals squared. Here we have x minus x bar, that quantity squared, and then white's numerator, is the sum of this. So you can break that equation up into several columns to make it a little bit easier to calculate. And then down in the green box is this, just the printout of the steps showing that actual correction. Okay, and faster way that can be done anytime the variance can be done when the form of variance or the form of heteroskedasticity is known, even in multiple regression. You just have to know which variable is causing the problem, is GLS, which is generalized least squares. So you transform your data from heteroskedastic to homoskedastic, which is obviously better because it means you're no longer violating an assumption, so you don't really have to make any individual corrections. You'll be able to read off your printouts, your coefficients, your standard errors. All of those will be nice and easy, same interpretations as you would get from a normal regression. Also, the standard errors are lower and the confidence intervals are smaller than they would be if you used White's corrections. So GLS is generally considered to be the superior way to go through and make these corrections. And I have a video that shows you how to run this in both Excel and SPSS. So the steps that are written here are for Excel: create a column, which is going to be your intercept column, 1 over the square root of x, regress the corrected x by dividing them, or correct the x's and y's by dividing them by the square root of x. Now, be careful. You can do this for both simple and multiple regression. But in multiple regression, this can only be done when you know which variable is causing the heteroskedastic problem. So you correct for the variable causing the problem. So this is why you needed to plot each independent variable against those residuals or standardized residuals to look for that cone-shaped pattern. So you'd see maybe x1 doesn't have a cone-shaped pattern. I don't need to make any correction there. But x2 does have that cone-shaped pattern. I do need to make that correction. So be really careful. You would have to divide all of your independent variables by 1 over the square root of the independent variable causing the problem, by 1 over the square root of the one that you need to do the correction on. Then you would run the regression. So in SPSS, you're just going to, you create this new column by creating a new variable. And you don't have to do anything about suppressing the intercept or anything like that. In Excel, you will need to suppress the constant to be equal to 0, and then this 1 over the square root of x will be your new intercept column. But then when you run the regression, you can just go through and interpret everything normally. So you can see here was the new version of that regression. It has, you can see the intercept was suppressed to be 0, but we created that new intercept column and we have that corrected x. And then you can just go through and do all of these interpretations normally. So for each additional month, I predict that sales will increase by 72.77. I'm 95% confident that for each additional month, sales will increase by between 68.17 and, I don't know, some really, really big number over there. They seem to have run together. But, you would be able to read that off of there, and then I can look at this p-value here and say I'm 95% confident that months, which is my x here corrected, do have a statistically significant impact on sales. I can say that roughly 93% of the variation in sales is explained by the variation in months. So I can do all of my general normal interpretations. Now, there is a huge literature on heteroscedasticity. So here are all the basic general corrections that can be done. Really, number 4 is what is going to be most often done in practice, which is just running GLS. Assumption 3 is that the errors are normally distributed. Normality is important because outliers exert leverage. Now, what is leverage? Besides a cool TV show on TNT. Well, what do they do on that cool TV show? They get information on people, and then they trick them, and they get them to do what they want. So that's, they have influence over those people, and that influence leads to a result. We're using the same kind of analogy here with our data. Our outliers are some observations that exert too much influence and therefore pull the results in their direction. If we have too many outliers or outliers that are too influential, then our errors aren't really normal and our results can be skewed in one direction or another. So if a point has too much influence in determining the y-hat equation, then its prediction it doesn't fit particularly well. So how would I do this? The first one is the visual or visual-ish method. We know from our standard normal distribution that 68% lies within 1 standard deviation, 95% lies within 2 standard deviations, and 99% should lie within 3 standard deviations. Well, when I plot my normal, my standardized residuals, they take that standard error into account. So 68% should fall, of the standardized residuals should fall between -1 and +1. 95% should fall between -2 and +2, and 99% should fall within -3 and +3. So my visual or visual-ish method, I plot those standardized residuals against my predicted values, and I check that COUNTIF function, do 95% fall within -2 and +2? Do 99% fall within -3 and +3? So I can examine that. Here's the example using my ComNodes 6 data, which gives me information on 14 communications networks. Here I'm looking at their cost based on the number of ports and the amount of bandwidth. And I can see my standardized residuals there. I can't really tell just by looking at them if there's a real pattern. So I'm going to go and I'm going to see, do any of them fall outside? I mean, I can look and I don't see anything out of +2. I have a residual that's down here. It's a little bit less than -2, but not outside of -3. So who knows whether it's really a problem. I can just go through and do that COUNTIF, and yeah, everything looks absolutely fine. I should have 95% within -2 and +2, and I have roughly 93%. I should have 99% within -3 and +3, and I have 100%. So this one's looking like it's okay. The statistical measures, on the other hand, I have 3 of them. Leverage, the D-fit statistic, and then Cook's D. So leverage measures how far an observation is from the others in terms of the independent variable. It's high if it's greater than 2 times the quantity k plus 1, where k is the number of independent variables, divided by n. So it basically tells you how spread out is this one from all of the others that we're looking at. The D-fit statistic examines the combined impact of that observation on the fitted values, and its comparison is 2 times the square root of the quantity k plus 1 divided by n. The D-fit statistic shows changes in the predicted value if the observation were deleted. And then Cook's D is the most specific. It's a function of residuals, leverage, and the model's mean square standard error. So it's going to be taking into account both the error terms and that leverage term as well. So here are the an observation is too influential if its value is greater than, and now obviously you'd have to plug, these values, these cutoff terms are going to be different for each model that you run, depending on the number of independent variables you have and the number of observations in your model. Here are the steps in SPSS, and I am also going to give you the steps in Excel, but I would highly, highly suggest that you just run this in SPSS because it's just going to spit out these numbers and it's a hell of a lot easier. You can just literally check off standardized defits, cooks, and leverage values, and the values will appear in the data editor. So not on the regular output, but they appear in the data editor, and you would just have to compare them to those influential cutoff values. If you want to do it in SPSS, or I'm sorry, if you want to do it in Excel, you have the formulas. Here's the printout of how to go through and do that, and there is a video showing you this. The way I did it was by creating several individual columns. So here's the output in SPSS, where the first one is cooks D, then leverage, then the standardized defits. Here are the steps to get the defits in SPSS. So here first the blue are the leverage statistics and the green are the defit statistics. So several steps, but you have the equation. So it is definitely possible to go through and do that in Excel, and you do have the equations for that. So corrections, if you find that the errors are not normally distributed, what can you do? It doesn't necessarily, normality is not necessary if you're making inferences with large sample sizes. So you could just be like, okay, it's all right. You know what? I have like 500 observations, so they're not normal. Whatever, that's fine. But if you have a small sample size, then yes, you will need to make some sort of correction. What do? The easiest way to make a correction, identify the outlier and remove it. So if you fail any of those tests, just highlight that observation, click delete, and then run your regression again. So this observation is an outlier, it's too influential, it's skewing my results. I'm just going to say, oh, it was a mistake, it was something random, it shouldn't have been included, and I'm going to take it out. So that's how we make that correction. Assumption number 4 is that the errors are independent of one another. So a violation of this would be autocorrelation in your errors. If disturbances tend to stay at the same level over a consecutive observations or over all of your model, then the model inferences may be slightly misleading. This often happens in time series data. When the residuals exhibit autocorrelation, the regression coefficients are unbiased, meaning that you can still, you still have your betas, and the interpretation of the beta is fine. But again, the standard errors, the t-values, and hence the p-statistics and the confidence intervals, all of them are going to be off. So the first one we usually test for is first-order autocorrelation. So this first-order autocorrelation, this equation is saying my error is equal to some portion of the previous error. And if we find that that's true, then there is autocorrelation and there is a problem. Now, this is first order autocorrelation because it's referring back to the previous error. It would be second order autocorrelation if it referred back to 2 errors beforehand, or third order autocorrelation if it referred back to 3 errors beforehand, and so on and so forth. So HO is that there is no autocorrelation. This rho value is equal to 0, meaning there is no impact, or if rho is not equal to 0, then there is some sort of relationship. So HO, there is no autocorrelation, and then HA, autocorrelation is present, and we would need to fix it. So again, the first method is the visual method, so plot the disturbances for each independent variable against the residuals, and you should see no pattern. If you do see a pattern, what are you looking for? Well, you're looking for a trend over time. That would be the issue that you'd be seeing. And the way we're going to test this is the Durbin-Watson statistic. Now, I have the equation for you, and it is testing specifically for first order autocorrelation, though you could change this for higher orders. Unlike the other tests, there's no when we're doing our cutoff values or something, you can't say, look at a p-value compared to 0.05 or a specific number that I just have to calculate. You will need to look at tables. So the tables are going to be provided for you, and there is a link on in the Chapter 6 page on Canvas to show you what these tables are. So if D is less than DL, which is the lower limit of the Durbin-Watson statistic, they reject HO and conclude there is positive autocorrelation. If D is greater than DU, then do not reject HO and conclude there is no positive autocorrelation. But if it's in between DL and DU, so the upper and lower bounds of that statistic, then the test is going to be inconclusive. The tables are given to you. It's table B7 on page B11 in the appendices of your textbook. The values range from 1 to 4. And again, I do have a link to the PDF of the tables provided on the Canvas page. So here are the steps in SPSS, and you literally just click under residuals, click Durbin-Watson, and it will go through and calculate that for you. In Excel, you go through and you follow that formula. So you get the DW numerator and denominator, then just divide those two and compare your value to what you find in the tables. So here's the example using sales advertising data. So 36 years worth of annual sales data and advertising expenditures. And our decision rule, reject if D is less than 1.41. Do not reject if greater than 1.52, and inconclusive if between 1.41 and 1.52. And you can see in Excel we come up with 0.467. We get the same thing using SPSS. So here we would reject HO, and we would discover that there is autocorrelation in here, so that would tell us that assumption number 4 is violated. The way to fix it: find a missing variable to fix the problem. Well, that's saying clearly you missed something in your data, so there's another influential variable in there. Go ahead and find it and stick it in, and that will make all of your problems go away. That'll fix a lot of these issues. Unfortunately, if you knew what that variable was, you probably would have included it in the first place. So this is one of those like mathematical solutions where you're like, thanks, math guy, but in reality, that's not going to help me. You can transform the model using the row method. So, once you've identified that degree of autocorrelation, you can transform your independent variables to say, look, this, there is going to be a relationship in here. Let's just accept that and include that in the model. Or the most common, you can add a lagged observation of your dependent variable as another independent variable into your model. And that's the most common correction. So just literally have a lagged observation of your dependent variable. So, your previous observation of y, and then you'll add that in as an additional x variable into your regression.